An infinite sequence is a list of numbers that go on forever and follow a specific rule or pattern. So here are some ways we can represent infinite sequences where the subscript n goes from 1 to infinity. And in this example of an infinite sequence, which follows this rule, the numbers in the sequence can be represented on a real line or graphically. So what we have is 1, 1/2, 1/3, 1/4, 1/5, and so on. So you can see that for a large n, the numbers in the sequence get closer and closer to 0. And here is another example of a sequence that oscillates according to the powers of -1. So it looks something like this. To prove the limit of a sequence, the epsilon delta definition is used. So this states that the absolute value of a term in the sequence minus the limit is less than some small number epsilon for all n greater than some integer n. So for example, we can see that when n equals n, all the terms an beyond this number fall between the limit plus epsilon and the limit minus epsilon. So you can see this by rewriting this inequality as follows, and then adding L for all these terms, we obtain the following inequality. And you can see that graphically over here, where all the terms beyond n fall in this range. But typically we don't apply the epsilon delta rule, because we typically just want to find the limit of a sequence to determine if it converges. And we thereby apply the rules for limits that we learned earlier for functions. Let's prove the limit of this sequence. So the formal definition is that for every number greater than 0, then there exists an integer n such that for all n greater than n, the difference between every number in that sequence minus the limit is less than epsilon. So for example, if n equals 2, then every number in that sequence beyond 2 must fall within this region for the sequence to converge. So using the rule for our sequence, minus the limit we're trying to prove, and taking the absolute value, and this must be less than epsilon. So therefore, we obtain 1 on n is less than epsilon, and flipping this equation around, we get the following inequality. So therefore, if we choose epsilon is equal to 1/2, which is a good value to choose based on the behavior of this sequence, then basically n must be greater than 1/2. So therefore, for this value of n equals 2, every number in the sequence beyond 2 must be less than epsilon, and the sequence converges. Let's determine if the following sequence converges, and this is done in much the same way as when we evaluate the limits of functions, because this sequence behaves like a function, except these numbers are discrete integers. So what we do is multiply by the reciprocal of the fastest growing term in the numerator and denominator, so we end up with the following limit. And therefore, taking the limit of each term individually as n goes to infinity, the following terms go to 0. And therefore, our limit is 4/3. Let's determine if the following sequence converges. So again, we multiply by the reciprocal of the fastest growing term. And you can probably see, because the fastest growing term is in a numerator, the sequence is going to diverge. But let's continue to evaluate the limit, which we can now write in this form. And now we can take the limit of each of those terms as n goes to infinity. So these ones are going to basically drop out. And we end up with the result of 1 on 0. So therefore, the sequence diverges. Let's determine if the following sequence converges. Well, these numbers are discrete integers, as we can see, and the equivalent continuous function that passes through all these numbers in the sequence is x to the 1 on x. So these are real numbers as opposed to those integers, and now we can apply logarithms and exponential functions to evaluate the limit. So if we take e to the power of the natural log of the function, we obtain the following result, and we didn't alter the function. And due to the continuity of the exponential function, we can take the limit inside that exponential function. And applying rules for logarithms, we can write the natural log of x on x. And now we can recognize that as x approaches infinity, the term in the denominator grows faster than the term in the numerator, which you can verify using L'Hopital's rule. So we obtain e to the 0, which is equal to 1. And you can verify that this sequence converges to 1 by putting in large integers in your calculator. A series is basically the sum of all terms in a sequence. So here is a sequence, which is a list of numbers, and here is the series, which is the sum of all those numbers. So remember that to determine if the sequence converges, we take the limit as n approaches infinity. And if that limit is finite, then the sequence converges. But to determine if a series converges, we need to check if the sequence of partial sums converges. So here we take the limit of the nth partial sum as n approaches infinity, and if that's a finite value, then the series converges to this value. And we say that it has a sum s. So the sequence of partial sums can be defined as follows. So we have the first partial sum, and the second partial sum is a2, and the nth partial sum can be written as follows. And to actually check this limit, we need to find a closed form expression for the partial sum of the series. And we'll do that in an example. Let's find the closed form equation for the nth partial sum of the following series. Well, we can write the nth partial sum of this series as 1 over 3 to the 1 plus 1 over 3 squared, and so on, up to 3 to the n. And if we multiply this by a third, we obtain the following result. And now if we subtract the second equation from the first, we get 2/3 Sn on the left hand side. And on the right hand side, all these terms here in the middle are going to cancel. So what we're left with is 1/3 minus 1 over 3 to the n plus 1. And now if we multiply through by 3 and divide by 2, we obtain Sn is equal to 1/2 by 1 minus 1 on 3 to the n. And now you can test that this works by finding a few partial sums using this closed form equation. Given this nth partial sum for the following infinite series, determine if the series converges, and if so, find the sum of the series. So if the sequence of partial sums converges, then the series converges. And what we do is take the limit of the sequence of partial sums, and as n goes to infinity, we can observe that this term disappears, and the limit evaluates to 1/2, which is effectively the sum of this series. So be careful that you don't confuse sequences with series, because if you take the limit of the sequence, well, this is going to evaluate to 0, which is different to the limit of the series. Let's find the sum of the telescoping series. So I'll leave it to you to apply the method of partial fractions, and you can write the series in the following form. So the nth partial sum can be written as follows, and now we can group every two terms together, and then we can cancel out the like terms, so minus 1/2 plus 1/2, and so on. So this minus 1/4 has another quarter here, and this 1 on n corresponds to a minus 1 on n before it. So what we're left with, and taking the limit of the sequence of partial sums for this telescoping series, as n goes to infinity, well, we can see that this second term goes to 0, and therefore the limit evaluates to 1, and consequently the sum of the series is 1. A geometric series is a series with a constant ratio between each successive term, and this infinite geometric series can be written as a sum from n equals 0 to infinity. Now using this form, we can write the nth partial sum as follows, and if we multiply both sides by r, we obtain the following expression. And now if we subtract the second equation from the first, we obtain the following expression, and on the right hand side, you can see that all these terms are going to cancel, except a and ar to the n. Now if we factor out a and divide through by 1 minus r, we obtain the following result. Now we can observe that when the ratio r is less than 1, then this term here approaches 0 when n approaches infinity, and therefore the series converges with the following sum. Now if the absolute value of r is greater than 1, then we can see that this term goes to infinity, and therefore the series diverges. And if r is equal to 1, then we get a divide by 0 and the series diverges. Let's find the sum of the following infinite series, or state if it diverges. Well, we can see that the ratio between each successive term is constant and equal to a third. So therefore this is a geometric series. And if this series converges, then the sum is the coefficient a over 1 minus the ratio. So to write this expression in the form of the sum of the geometric series, we can assume a is equal to the first term, and then write the subsequent terms as multiples of 1/2. So what we get is 1/2 plus 1/2 by 1 on 3, and so on. And if we're writing this as a sum from n equals 0 to infinity, we have a multiplied by the ratio to the power of n. And therefore the sum is 1/2 over 1 minus a third. And you can simplify this as 1/2 over 2/3 or 3/4. Given the following infinite series, which is effectively the sum of the terms in the following sequence, and we can't always get a closed form expression for the nth partial sum of the series, so we need to introduce some tests to determine if the series converges or diverges. And one of these is the nth term test, which checks if a series diverges. So this test checks if the limit of the sequence, as n approaches infinity, is not equal to 0 or does not exist. And if one of those conditions is true, then the series diverges. Otherwise, the test is inconclusive. And really have a think about why that is. And we'll do a few examples to demonstrate the test. Let's determine if the following series diverge using the nth term test. And this is one of the tests that we use for infinite series, where there's no closed form equation for the partial sum. Well, this test tells us to take the limit of the sequence that corresponds to this series. And in this case, it's equal to 1, and because it's not equal to 0, the series diverges. Now if we take the same step for the next series, well, in this case, the limit is 0, so the test is inconclusive, because regardless of this sequence converging, the sequence of partial sums may converge or diverge. So this test only tells us if a series diverges. Now for the final series, this sequence keeps oscillating from 1 to -1, so the limit does not exist, and the series diverges. If a real function, f of x, is positive, continuous, and decreasing for x greater than or equal to some integer n, so as we can see that's true for this function, and an is a function of the integer n. So this describes the terms in the series. Then the series summed from n to infinity and the integral from n to infinity of the real function both converge or diverge. So if we look at this as the left Riemann sum, you have this rectangle with a height an according to this series, and these rectangles all have widths of 1 when you're incrementing n by 1 in this series. So the integral gives the area under the curve described by f of x from n to infinity, and that's smaller than the area given by the series. So therefore if the series converges, then the integral that gives the smaller area also converges. And conversely, if the integral diverges, then so does the series. Let's determine if the following series converges using the integral test. Well, from this series, we can define a function that's positive, continuous, and decreasing from 1 to infinity. And because this is an improper integral, we can take the limit of a dummy variable and replace infinity, and now we can evaluate this integral and then take the limit. So what we get is the following limit. So remember, when y is equal to the arctan of x, we can take tan of both sides, and we can rewrite tan as sine y on cosine y. So if x approaches infinity, then y must approach pi on 2. So therefore this term evaluates to pi on 2, and this term is finite, so therefore this integral converges, and because this integral converges, this series also converges by the integral test. In addition to the geometric series, we'll encounter other types of series known as the harmonic series. So this series is called the harmonic p series, where the terms are the reciprocals of n to the power of p. And for the special case, when p equals 1, then we have the harmonic series. And this is represented graphically over here. So if we expand a few terms, then we can see that the harmonic series gives the area enclosed by these rectangles. And another type of series we'll encounter is the alternating harmonic series. So in this case you'll have powers of -1 multiplied by 1 on n. So this will give 1 minus a half plus a third and so on. Let's derive the convergence conditions for a harmonic p series. So we can define a function that's positive, continuous, and decreasing from 1 to infinity, and integrate this with respect to x. And given that this is an improper integral, we can take the limit of a dummy variable. So if we evaluate this integral, we'd obtain the following limit, or we can write this in a neater form of 1 minus p. And therefore, the limit is written as follows. Now for the special case, where p is less than 1, then you'll have b to a positive power, and as b approaches infinity, so does the integral. So the integral diverges. And if p is equal to 1, then you have a divide by 0, and the integral also diverges. And if p is greater than 1, then what you'll get is reciprocals of b, and as b approaches infinity, the integral therefore converges. And by the integral test, these convergence conditions apply to the series. Let's determine if the harmonic series converges using the integral test. So we can see geometrically that the series gives the approximation to the area under the curve 1 on x using the left Riemann sum with a rectangle width of 1. So the function is positive, continuous, and decreasing from 1 to infinity. So we can use the integral test, which gives the area under the actual curve 1 on x. And if this integral diverges, then so does the series, because that gives a larger area than that under the curve. So we can evaluate this improper integral using dummy variables, and this gives the following result. And as we can see, the natural log of 1 is 0, and as b goes to infinity, so does the natural log of b, so therefore the series diverges. So even though these terms keep getting smaller and smaller, the rate of convergence is very slow. So the sequence of partial sums will never converge. Let's determine if the following series converges using the integral test. So we can see that the function is positive, decreasing, and continuous on the interval from 1 to infinity. So we're going to get a positive area under the curve, and we can apply the integral test. So therefore we integrate the equivalent real function from 1 to infinity, and because it's an improper integral, we can introduce dummy variables. And that gives the following result. And then evaluating the integral at those limits of integration, we can see that as b goes to infinity, this term goes to 0, and the limit evaluates to 1. So the series converges. The comparison test can be used to determine if an infinite series an converges by comparing it against another series bn whose convergence is known. So for example, the geometric and harmonic p series, which are typically used to compare against in this test. So given that all the terms in this series are positive, and if all the terms in series A are smaller than or equal to all the terms in series B, for all n greater than some integer, and Bn converges, then An also converges. So really have to think about this. And in contrast, if all the terms in series A are greater than or equal to all the terms in series B, for all n greater than n, and the series Bn diverges, then the series A also diverges. And we'll apply this to practice problems. The limit comparison test is particularly useful for a series A, where an is a rational function of n. And again, we compare this infinite series against an infinite series whose convergence is already known, like the geometric and harmonic p series, which are typical. Now given these two series have all positive terms, for all n greater than some positive integer, and bn is not equal to 0 because we can't divide by 0, we have three rules in a limit comparison test. And these take some getting used to by applying them to different examples. So if the ratio of an and bn as n approaches infinity is equal to a positive number, then both series an and bn converge or diverge. And for the second rule, if the limit of an on bn as n approaches infinity is equal to 0, and bn converges, then an also converges. And if the limit of an on bn as n approaches infinity is unbounded, and bn diverges, then an also diverges. Determine if the following series converges using the comparison test. So as n becomes very large, this term will dominate, and we can compare this series with a series that we already know. So that's going to be the harmonic p series, and we can take the constants outside the series, so this can be written as follows. And this here is a harmonic p series with the exponent p greater than 1. So we know that this series converges. And if we designate these terms in the series as an, and these terms in the series as bn, then we can see that these terms here are always going to be smaller than bn for all n. So therefore, due to this condition, and because our series here converges, then this series also converges by the comparison test. Let's determine if this series converges using the comparison test. So for a large n, the first term is dominant, and we might write this as the following series. And now we know this here is a harmonic p series with the exponent p being less than 1, so we know that this diverges. And therefore by comparison, we can see that the terms in the first series are going to be greater than those terms in that second series for all n, because we're subtracting 1 in a denominator. So therefore, because of this condition, and because this series diverges, then this series also diverges by comparison. Let's determine if the following series converges using the comparison test. So for a large n, this term dominates, and we may write the following series to compare against. And you may recognize this as the geometric series if we expand a few terms. So the general form of the geometric series is as follows, where a is equal to 1/3 and the ratio r is also equal to 1/3. So because the absolute value of the ratio is less than 1, then this geometric series converges. Now if we compare each term of both series, we can see that the terms in the first series are always less than the terms in the second series, for all n. So because of this condition, and because this series converges, then this series here also converges. Let's determine if the following series converges using the comparison test. So as n becomes large, we can see this term is dominant, and we can construct the following series to compare against. And if you expand this series, so we get 1 on 2 plus 1 on 2 squared, and so on. So you may now recognize this as a geometric series with a ratio of 1/2 and a equals 1/2. So because the absolute value of the ratio is less than 1, then we know this series converges. Now the terms in our series here are always less than the terms in the geometric series for all n. So because of this condition, and because this series converges, then this series also converges. Let's determine if the following series converges using the limit comparison test. And this test is good to use when we have a rational polynomial. Now for a large n, the n cubed term will dominate in the denominator, so we can choose the following series to compare against. So we have 3n on n cubed, which is 3 on n squared. And now we take the limit as n approaches infinity of the ratio of both terms in both series. And now we can see the 3's cancel and the n squared goes in the numerator. So we get the following expression. And this evaluates to a limit of 1. So because we've got a positive number, so then rule 1 of this test applies, meaning that both series either converge or diverge. So if we check this series over here and just take the constant outside, well, as we can see, this is a harmonic p series with the exponent greater than 1. So we know that this series converges, and therefore both series converge by the limit comparison test. Let's check if the following series converges by the limit comparison test. Well, for a large n, n squared in the denominator dominates, so this becomes 2n on n squared, or 2 on n. So we choose this series to compare against. And now we take the limit as n approaches infinity of the ratio of both terms in those series. So using a bit of algebra, this can be written as follows. And this evaluates to 1, which is greater than 0. So rule 1 of this test applies, which means that both series converge or diverge. So recognizing this series, by taking the constant out of the sum, well, this is a harmonic p series with an exponent of 1. So we know that this diverges. And therefore, by the limit comparison test, this series also diverges. Let's check if this series converges by the limit comparison test. Well, for a large n, this term dominates in a denominator, so we may compare against the following series. So that will be 3 on 6 to the power of n, or 1/2 to the n. And now we take the limit as n approaches infinity of the ratio of both terms in those series. And doing a bit of algebra, this simplifies as follows. And therefore this limit evaluates to 1, which is a finite number greater than 0, so both series either converge or diverge. And if you expand this series, well, this is a geometric series with a ratio of 1/2. And given that the absolute value of the ratio is less than 1, we know this geometric series converges. And by the limit comparison test, this series also converges. Determine if the following series converges using the limit comparison test. Well, we know that the natural log grows more slowly than n to a positive exponent, as n goes to infinity. So we can conveniently choose the positive exponent of 1/2 and write the following series to compare against. So it'll be n to the half on n to the 7 on 2, which is 1 on n cubed. And now we can take the limit as n approaches infinity of the ratio of both terms in those series. And doing a bit of algebra, this simplifies as follows. So n to the half grows faster than the natural log of n as n goes to infinity. Well, you can verify this using L'Hopital's rule, so we get a limit of 0. So the second rule of the test applies, meaning if this series converges, then so does this series. Well, this is a harmonic p series with an exponent of 3, which is greater than 1, so we know this series converges. And therefore this series also converges by the limit comparison test. The alternating series test is used to determine if an alternating series of positive and negative terms converges. So what we do is designate this as AN, and BN is the absolute value or the positive values of AN. So the first rule states that for this alternating series to converge, BN must be positive for all n. And the next rule states that the current term in the series must be greater than or equal to the next term in the series for all n greater than some integer n, meaning these terms are decreasing. And the third rule states that Bn must approach 0 as n approaches infinity. And we'll get some practice in applying these rules. Let's apply the alternating series test to determine if this converges. Well, we denote these terms in the series as An, and these terms 1 on n as Bn, which is equal to the absolute value of An. So first we check if Bn is greater than 0 for all n, which is true, and the next rule states that Bn must be greater than Bn plus 1 for all n greater than some integer n. Well, as we can see, 1 on n is always greater than 1 on n plus 1. So this is also true. And the third rule states that the limit of Bn as n goes to infinity is equal to 0. And this is also true. Then this series converges by the alternating series test. And interestingly, we found previously that the harmonic series diverges. The ratio test is useful when the terms in the series contain expressions of factorials of n, or expressions raised to a power involving n. Given an infinite series A, where all the terms are positive, and the limit of the ratio of the next term in the series to the current term in the series as n approaches infinity is equal to rho, then the ratio test has 3 rules. So if rho is less than 1, the series converges. If rho is greater than 1, the series diverges. And if rho is equal to 1, then the test is inconclusive. So remember the geometric series, which you can write as follows after expanding a few terms. Then you can see that the ratio test verifies that the ratio of the geometric series is constant. And therefore, if this ratio is less than 1, the series converges, which is consistent with the convergence conditions that we derived for the geometric series. Let's use the ratio test to determine if this series converges. So we take the limit as n goes to infinity of the ratio of the next term in the series to the current term in the series. And doing a bit of algebra, we can write this as follows. And the second term is 1/2, so we can write the limit as follows. And therefore the limit evaluates to 1, so we obtain 1/2. And because this value is less than 1, then the series converges by the ratio test. Let's determine if this series converges by the ratio test. So you may recognize that this is a harmonic P series with P greater than 1, so we know that it's going to converge. But let's see if the ratio test can come to the same conclusion. So we take the limit as n goes to infinity of the ratio of the next term in the series to the current term in the series. And doing a bit of algebra, we obtain the following limit. So the 3's cancel, and the fastest growing term is n squared in the numerator and denominator. So this evaluates to 1. So because we got rho equals 1, then this test is inconclusive, and the ratio test typically works when you have n in the exponent and factorials. Determine if the following series converges using the ratio test. So we take the limit as n approaches infinity of the ratio of the next term in the series to the current term. And noting that n factorial here is n minus 1 plus 1 factorial. And using a bit of algebra, and 3 to the n plus 1 on 3 to the n is 3, and n minus 1 factorial can be expanded as follows. And similarly, n factorial can be expanded as follows. So we can see that all the terms cancel except for n. So we can rewrite this limit as follows, and therefore this evaluates to 0. So because we obtain rho equals 0, which is less than 1, then this series converges by the ratio test. If the series of absolute values of the terms in this series converges, then this series here converges absolutely. Otherwise, we say that this series converges conditionally. So effectively, a series can be absolutely convergent, conditionally convergent, or divergent. If a series A converges absolutely, and the sequence B is any arrangement of the sequence A, meaning that we can rearrange and group the terms in A in any order. Then the series B will also converge absolutely, and the sum of series B will be equal to the sum of series A. And we'll show this in an example problem. Let's determine if this series converges conditionally, absolutely, or diverges. Well, we designate this term in the series as AN, and this term in the series as BN, which is the absolute value of AN. And now we check if the series AN converges conditionally using the alternating series test. So in this test we just check if Bn is greater than 0 for all n, and then we check if Bn is greater than Bn plus 1 for all n above some integer. Well, as we can see, 1 on n is greater than 1 on n plus 1 for all n. And then we check if the limit as n goes to infinity of Bn is equal to 0, which is the case. So in other words, so far the series AN converges conditionally. Now to check for absolute convergence, we need to check if the series Bn, which is the absolute value of AN, converges. Well, we know that this is a harmonic series and that it diverges, so therefore this series converges conditionally. Let's check if this alternating series converges conditionally, absolutely, or diverges. So again, we designate this series as AN and the series of these terms as Bn, which is the absolute value of AN. And now using the alternating series test, we can see that 1 on n squared is greater than 0 for all n, and the current terms in the series are always greater than the next terms in a series for all n greater than some integer. And we also have the limit as n goes to infinity of 1 on n squared equal to 0, so the series satisfies the check for conditional convergence. And now to check if it converges absolutely, we take the series Bn, and we recognize that this is a harmonic p-series with the exponent greater than 1, so this series converges, and therefore this series converges absolutely. Let's determine if the following alternating series converges conditionally, absolutely, or diverges. So we designate these terms in the series as AN and these terms as Bn, which is the absolute value of AN. And using the alternating series test, we can see that Bn is greater than 0 for all n, and we can also see that the current terms in the series are greater than the next terms in the series for all n greater than some integer. And we can also see that the limit as n goes to infinity of Bn is also 0. So the series satisfy the checks for conditional convergence, and that the check if the series converges absolutely if the series of Bn terms converges. And you can check that using the limit comparison test, and I'll leave that for you to check that if this series converges, then this series would converge absolutely. And post your answer in the comments. The following series converges absolutely, and we're asked to show that by rearranging the terms, the resulting series has the same sum. Well, this is an alternating geometric series, and the most obvious way of rearranging this series is by grouping the positive and negative terms together. So this is one series, and this here is another geometric series where we factor out the negative sign. So this geometric series has a value a equals a half and a ratio of minus a half, and this geometric series has a is equal to a half and the ratio between the terms is 1 over 2 squared. And for this series over here, we can see that a is equal to 1 on 2 squared and the ratio is also 1 on 2 squared. So really think about this. And given that absolute value of all the ratios is less than 1, then every one of those series has a sum, and now you can verify that this series and the difference of the sums between these two series has the same value. So post your answer in the comments. If the alternating series A converges, then the nth partial sum, which is equal to the alternating sum of the B terms, approximates the sum of the series with some error. And this error is equal to the difference between the sum of the series and the partial sum, which is bounded by the next term in the series. So effectively in this case, the next term in the series will be minus 1 to the power of n plus 2 multiplied by bn plus 1. And this here is what we call the error bound. So effectively this error cannot be greater than the error bound. Find the error using the partial sum up to n equals 3 and show that it's less than the error bound. So we can expand the series as follows. And in this geometric series, a is equal to 1 and the ratio between terms is minus a third. And therefore the series converges, because the absolute value of the ratio is less than 1. So the sum of the series is equal to a on 1 minus the ratio, which is 1 on 4/3 or 3/4. Now you can compute the sum up to n equals 3, so that will be up to here. And I'm just going to write down the result, so that will be 20 on 27. And now to find the error, we'll just take the absolute value of the difference between the sum and the sum using 4 terms, up to n equals 3. So subtracting these two, we get the following result, and checking that this is less than the error bound. So the error bound is simply the next term in the series. So as we can see, this is true. A Taylor polynomial with a degree of k can be written as the sum of the derivatives of a function f of x evaluated at x equals a on the factorial of n multiplied by the difference between x and a to the power of n. So we said that this Taylor polynomial for the function f is centered at x equals a, and it can thereby be used to approximate the values of the function f near x equals a. So in this case, a is equal to pi on 2, and our function is cosine x. And you can see that when we use a 0th order polynomial, we have a really bad approximation to the function, and we can see that the linear approximation approximates cosine x better near x equals a, and as you keep using more terms of the Taylor polynomial, you get an even better approximation, even further out from a. Let's find the 4th order Taylor polynomial approximation for cosine x about x equals pi on 2. So our function is cosine x, and we keep taking derivatives up to the 4th order derivative. And now we evaluate the function and its derivatives at x equals pi on 2, and now we can write our 4th order Taylor polynomial approximation for our function. So that would be minus 1 on 1 factorial by x minus pi on 2, and we've also only got a 3rd order term. So that would be 1 on 3 factorial by x minus pi on 2 cubed, and the rest of the terms are 0. So as we can see, for a 1st order Taylor polynomial approximation, we have a straight line, so the linear approximation is very good, close to pi on 2, and it gets worse as you move away, as we can see. But the 4th order polynomial approximation has a cubic term, so that gives a much better approximation to the cosine function. Given the Taylor polynomial with an order n that's used to approximate a function f of x, and the polynomial approximation is centered around x equals a, then the remainder or error of the approximation is the absolute value of the difference between the function and the polynomial approximation. And this error is bounded by the next term in the Taylor series. So the Taylor polynomial is the partial sum of the Taylor series. So this expression on the right is the Lagrange error bound, and it's basically the next term in the Taylor series, except that the derivative is evaluated at some value c, which is between a and x. So in this example, a is equal to pi on 2, and suppose we want to approximate the function somewhere here at x equals pi. So the n plus 1 derivative will have the largest value between pi on 2 and pi. And we'll see that in worked examples. Approximate cosine pi using a 2nd order Taylor polynomial about a equals pi on 2, and verify that the error is less than the error bound. So we take the derivatives of cosine x and evaluate them at pi on 2. So the error is basically the remainder of our 2nd order polynomial approximation. So that's the difference between the exact value of the function and our polynomial approximation. And that must be less than or equal to our error bound. So for the error bound, we evaluate the derivative of our next term at some value c, and this value c is between a and x, because we want to maximize the error bound. So our next term in the polynomial is sine c on 3 factorial by x minus pi on 2 cubed. Now to maximize the error bound, we choose c is equal to pi on 2, and then substituting for x equals pi, we obtain the following result. And if you substitute f of x and x in the polynomial approximation, you'll obtain the error. So as you can see, the error is less than the error bound. Approximate the natural log of 1.3 using a 3rd order Taylor polynomial about a equals 0, and verify that the error is less than the error bound. So here we have a Maclaurin polynomial approximation, so we need to be careful not to take our function as a natural log of 0. And now we take the derivatives up to the 3rd order and evaluate these at x equals 0. And now we can write our 3rd order Taylor polynomial approximation. And now to find the error, which is the remainder, that's the difference between a function and a polynomial approximation. And that must be less than or equal to the error bound. So for the error bound, we evaluate the derivative of our next term of the polynomial at some value c. And in this case, x is going to be 0.3 and a equals 0, so c is between a and x. So to maximize the error bound, c is in a denominator, so we take it as 0, and x is 0.3. So if we calculate this out, and if you substitute x in the polynomial and subtract the result from the natural log of 1.3, you obtain the following result for the error, which you can see is less than the error bound. Approximate 1.3 to the 512 using a third order Maclaurin polynomial for the following function and verify that the error is less than the error bound. So this is our function, and differentiating it 3 times and evaluating these at x equals a equals 0. So our third order Maclaurin polynomial approximation can be written as follows. So now to obtain the error in our approximation, that's the remainder, and that must be less than or equal to the error bound. Now to obtain the error bound, we obtain the derivative of the next term in the series and evaluate it at some value c, where c is between a and x. So in this case, given our function here, x must be 0.1 to obtain 1.3. So our error bound can be written as follows. So because c is in a denominator, we choose c is equal to 0 to maximize the error bound, and x is 0.1, and calculating this out. Now to obtain the error, we substitute x equals 0.1 in our polynomial and subtract it from the exact value. So calculating that out, so we can see that the error is less than the error bound. A power series has the following form, where the coefficients and a are real numbers, and here we say the power series expansion is centered around a. For the case where the power series is centered on a equals 0, the power series has the following form, which is expanded as follows, and for the further special case, where all the coefficients are 1, then this is written as follows. So this form of the power series is a geometric series, where the ratio is x, and the constant is 1. So therefore the geometric series has the following sum, of 1 on 1 minus x. And here we have several terms, so the more terms we introduce, the better that the series approximates the exact sum of the geometric series. And note that the geometric series converges when the absolute value of the ratio is less than 1. So the interval of convergence is from -1 to 1. And the radius of convergence is 1, which is half the interval of convergence. Given the following power series, it can converge in one of the following ways. So number 1 is the power series can converge over an interval. So effectively, the interval of convergence for this power series centered on x equals a is a minus r to a plus r, where r is called the radius of convergence. So basically just add a to all these terms. Then outside this interval of convergence, the power series diverges, and at the endpoints of the interval, the power series may converge or diverge. So we need to test those endpoints separately. Now the second way a power series can converge is for all values of x. So in this case, the radius of convergence is infinite, and the interval of convergence is from -infinity to infinity. And the third way a power series can converge is at a single point. So in this case, the radius of convergence is equal to 0, and the power series converges at a particular x value and diverges for all other x values. To determine the radius of convergence for a power series, we use the ratio test. So we take the limit as n approaches infinity of the absolute value of the next term in the series to the current term in the series. And we take the absolute value because this expression can be negative. So therefore what we end up with is the limit as n approaches infinity of the absolute value of the following expression. And factoring out the absolute value of x minus a, and by the ratio test, this must be less than 1 for the power series to converge. So this is going to give us the radius of convergence and the open interval of convergence. And then we test the endpoints of the interval after that, which looks something like this for a power series centered on x equals a. So recall the convergence conditions. We can have convergence over an interval at a single point, or for all values of x from -infinity to infinity. And we'll see that in a few examples. If a power series has a radius of convergence greater than 0, then the series defines the following function. On the open interval, from a minus the radius of convergence to a plus the radius of convergence. And f of x has derivatives of all orders which converge inside this interval. And we'll see that this condition means that the power series is the Taylor series of the function, to which it converges over the open interval. Now if we differentiate the series term by term, we obtain the following expression. And differentiating again, and note when n equals 0, this expression is 0, So we can sum from n equals 1. And when n equals 0 and n equals 1, the first two terms are 0, so we can sum from 2. And the radius of convergence of the series defining these derivatives is the same as the radius of convergence of the original power series. And I encourage you to show that using the ratio test. If a function is defined by a power series centered on x equals a, which converges on the open interval from a minus r to a plus r, where the radius of convergence is greater than 0, then the following power series converges, and the integral of the function also converges on this interval. And the radius of convergence of this series is the same as the radius of convergence as the original power series. So here we've integrated the terms in the series using the power rule for integration. And I encourage you to show that the radius of convergence of this power series is the same as the radius of convergence as this power series using the ratio test. And term-by-term integration can be used to identify a function represented by a power series or obtain a power series representation of a function. So they're the typical uses of this theorem. Given the following power series expansion about x equals 0 with constant coefficients of 1 for all n, so in other words, this power series can be expanded as follows. We're asked to find the radius and interval of convergence and describe the convergence using the curves below. Well, this is a geometric series with the ratio of x between the terms, so this only converges if the absolute value of the ratio is less than 1. So therefore this gives us an interval of convergence between minus 1 and 1. And the radius of convergence is half of the interval of convergence. And now according to these curves, when we use one term, we get a horizontal line. And as we increase the number of terms that we use in the series, we get a better and better approximation to this sum. Okay, so for n equals 1 we get a linear approximation. For n equals 2 we get a parabolic approximation. So you can see that the series is going to converge to the exact sum. Let's find the radius and interval of convergence for the following series. And we recognize this is a power series because we can write it as follows. And now we check for absolute convergence using the ratio test. So we take the absolute value of the ratio of the next term in the series to the current term in the series. And we take the absolute value because x can be negative, and the ratio test applies only if this ratio is positive. And now doing a bit of algebra, and given that n is positive, and the first term evaluates to x, so we can take the absolute value of x outside the limit. And with these factorials, all terms cancel except n plus 1 in the denominator. So this can be written as follows. And therefore the limit evaluates to 0. So by the ratio test, rho is always less than 1. So that means the series converges for all values of x. So effectively, the radius of convergence is infinity, and the interval of convergence is minus infinity to infinity. Let's find the radius and interval of convergence for the following power series. So again, we check for absolute convergence using the ratio test. So we take the ratio of the next term in the series to the current term in the series. And we check for absolute convergence because x can be negative. So because n is positive, and x to the n plus 1 on x to the n evaluates to x, we can take the absolute value of x outside the limit and take the limit of the ratio of the factorials. So with these factorials, only n plus 2 is not going to cancel, and all the other terms are going to cancel. So therefore this limit is unbounded, and recall that for the ratio test, rho must be less than 1 for the series to converge. So therefore rho is less than 1 only for x equals 0. So for x equals 0, the series converges, and when x is not 0, the series diverges. So therefore the series converges only at a specific point, and therefore the radius of convergence is 0. Let's find the radius and interval of convergence for the following power series. And again, checking for absolute convergence using the ratio test. So taking the ratio of the next term in the series to the current term in the series. And doing a bit of algebra. And because n is positive, we can take the absolute value of x outside the limit. And therefore the limit evaluates to 1. So this series converges when the absolute value of x is less than 1. Or this can be written as minus 1 less than x less than 1. So therefore the radius of convergence is half the interval of convergence. And now we need to check the individual endpoints of the interval. So for x equals minus 1, we just substitute x equals minus 1 in that series. And we recognize that this is an alternating harmonic series, so we know this converges. So therefore the series converges at x equals negative 1. And now if we substitute x equals 1 in that series, Well, 1 to the power of n is always 1, so therefore this is a harmonic series, and we know it diverges. And therefore the interval of convergence is minus 1 inclusive to 1, where the interval is open. Let's determine the radius and interval of convergence for the following power series. So again, using the ratio test, we take the limit of the ratio of the next term to the current term in the series. And then doing a bit of algebra and taking the absolute value. So for the series to converge, we have 2 by the absolute value of x must be less than 1 by the ratio test. And therefore, we obtain minus a half less than x less than a half. So the radius of convergence is 1/2 of the interval of convergence. So now we test the endpoints of the interval. So we substitute minus a half into the series. So that will be minus 2 by minus a half to the n, or 1 to the n on root n plus 1. And I'll leave it for you to verify that this diverges. And testing the second endpoint, so we'll just substitute 1/2 into the original power series. So that'll be minus 1 to the n on root n plus 1. And I'll leave it for you to also test if this series converges, and then you'll obtain the interval of convergence and post your answer in the comments. Determine the radius and interval of convergence for the following power series. So again, we test for absolute convergence using the ratio test, and then doing a bit of algebra, and the absolute value is going to cancel out the -1, and the absolute value of x squared is just x squared. So we can take that out of the limit, and then the limit's going to evaluate to 1. So for the series to converge, x squared must be less than 1, which is the same thing as minus 1 less than x less than 1. So the radius of convergence is half of the interval of convergence. And now we test the endpoints. So for x equals minus 1, we substitute back in the original power series. And therefore you get minus 1 to the power of 3n plus 1 in the numerator. So this is an alternating series, which satisfies the 3 conditions of the alternating series test. So the series converges at minus 1. And similarly, we substitute 1 into the original power series to test that endpoint of the interval. So 1 to the 2n plus 1 is 1. So this is another alternating series that converges. So verify that yourself, and you'll find that the interval of convergence is minus 1 to 1 inclusive. Let's find a power series, radius and interval of convergence for the first and second derivative of the following function. So we recognize that this is a sum of a geometric series with a equals 1 and a ratio of x. So we can write the function as follows. And now differentiating this function, we obtain the following series. And note that we take n equals 1 because this constant drops out. And differentiating again, we obtain a series for the second derivative. So we just use the power rule and differentiating term by term. And now we can test this derivative for absolute convergence using the ratio test, which gives the following result. And the limit evaluates to 1. So the derivative converges when the absolute value of x is less than 1. And therefore, the radius of convergence is 1. And the interval of convergence is open from minus 1 to 1. And if you follow the same step for the second derivative, you should obtain the same result. Let's find the analytical function given by the following series. So if we expand this series and differentiate each term, so we recognize the derivative is a geometric series with a equals 1 and a ratio of minus x squared between the terms. So therefore we get an analytical function for this geometric series of a over 1 minus the ratio squared. And now if you separate the variables and integrate both sides, well, what we get is the function is equal to the arctan of x plus the constant of integration. And if we recognize that f of 0 is equal to 0, because x appears in all these terms, so what you get is the constant of integration is also 0. And if you did your convergence checks on this series, which we've done previously, so you'll see this series converges on the closed interval from minus 1 to 1. And this is clear from the plots here. So as we increase the number of terms in the series, we get a better and better approximation to the arctan function, but only inside the interval of convergence from minus 1 to 1. A Taylor series is an infinite power series, and here we have the Taylor series expansion centered on x equals a. And recall that the Taylor polynomial has this form, but it's finite, so the Taylor polynomial for the function f of x is the partial sum of the Taylor series. So when we expand a few terms, and an example of a function that has derivatives of all orders is the exponential function. And here we have the Taylor series expansion centered on x equals 1. So as we use more terms in the Taylor series, you get a better approximation to the function until you get the exact value if you use an infinite number of terms. And when the Taylor series expansion is centered on x equals 0, that's called the Maclaurin series. And in subsequent videos, we'll see that the Maclaurin series for the special function 1 on 1 minus x is a geometric series And the Maclaurin series for elementary functions gives the foundation for constructing the Maclaurin series for other functions. Given a Taylor series expansion about x equals a, which can be written in this form, where f of x has derivatives of all orders at x equals a, we're asked to find a Taylor series of e to the x about a equals 1. So let's expand a few terms of this series, and given f of x is e to the x, well, all these derivatives are going to evaluate to e to the x. And evaluating these at x equals a equals 1, and then we can substitute these into this function. So as you can see, the more terms we use from the infinite series, we get a better and better approximation to the function e to the x, about x equals a equals 1. So the approximation is better, close to this value, using less terms of the Taylor series. Let's show that the Maclaurin series for the following function is a geometric series. So remember the form of the Maclaurin series. So we differentiate the function a number of times and evaluate the function and its derivatives at x equals 0. And you can see that these are factorials. And now we can write out our expansion, so that will be f of 0 plus the derivatives on the factorials by x to the power of n. And you can see that the derivatives are factorials themselves, so these are all going to cancel. So this gives us a geometric series with a constant of 1 and a ratio of x. And therefore the geometric series converges where the absolute value of the ratio is less than 1. And this is the sum of the geometric series, as we've seen before. Find the Maclaurin series of sine x. Well, a Maclaurin series is simply a Taylor series expansion about a equals 0. And that can be expanded as follows using a few terms in the series. And f of x is sine x, and we differentiate this a bunch of times up to the third derivative. And evaluating these at x equals a equals 0, and these derivatives just keep cycling. So now we can substitute back into the function where f of 0 and f dash dash of 0 is 0. So if you keep cycling the derivatives, the next one's going to be x to the 5 on 5 factorial and so on. And now we can write this as an infinite series. So we have minus 1 to the power of n, which cycles through positives and negatives. And then when n equals 0, 1, 2 and 3, we have x to the power of 1, 3 and so on. So that will be 2n plus 1. And then divide this by 2n plus 1 factorial. Because we have 1 factorial for n equals 0, 3 factorial for n equals 1 and so on. And that's our series. Let's find a Taylor series of cosine x about x equals 0. So f of x is equal to cosine x, and we differentiate this several times. And evaluating these at x equals 0, we're basically obtaining the Maclaurin series. And now we can write our function as follows. So we have 1 minus 1 on 2 factorial by x squared. And then these derivatives will keep cycling. So our next term is going to be plus x to the 4 on 4 factorial, and then minus x to the 6 on 6 factorial, and so on. So therefore we can write our function as an infinite series. So we have minus 1 to the power of n to flip between positives and negatives. And for n equals 0, 1 and so on, we have x to the power of 0, x squared and so on. So that will be x by 2n, as we can see. And that's divided by 2n factorial, because we have 0 factorial, 2 factorial and so on. And that's our Maclaurin series for cosine x. Let's prove Euler's formula using the Maclaurin series for the following elementary trig functions. So if we start off with f of x and take the derivatives several times and evaluate these at x equals 0, and now we can write out the Maclaurin series, then taking the next derivative, so these derivatives will just keep cycling back and forth. So next we're going to get 1 and then I and so on. And now we can group the real and imaginary terms together. And we've factored out the imaginary number. So as you can see, this here is cosine x, and this here is I sine x. We can find the power series of a function using term-by-term differentiation or integration, algebraic processes, substitutions and so on. And sometimes we can simply recognize that the function represents a geometric series. So here we have a constant of 1 and a ratio of x. And therefore we can write this function as a geometric series. So a is 1 multiplied by the ratio to the power of n. And we know that this series converges when the absolute value of the ratio is less than 1, and that gives the radius of convergence. And this tells us that the interval of convergence is from -1 to 1. And we'll do a few examples in the following videos. The power series representation of sine x is given here and we're asked to find the power series representation of cosine x. So remember that the derivative of sine x is cosine x. So we can either expand a few terms of this series and differentiate them one by one, or we can simply differentiate with respect to x. So we have minus 1 to the n, and then using the power rule for differentiation, we have 2n plus 1, and reduce the exponent by 1. So 2n plus 1 is going to cancel in the numerator and denominator, and we thereby obtain the following infinite series, which represents cosine x. And I encourage you to verify this by obtaining the Maclaurin series for cosine x. Let's find the power series representation of the following function. So we can say that it almost looks like a geometric series, so we can try some algebraic manipulation. So factoring out 3, and then we can write x squared on 3 in the numerator. So this looks like a geometric series where the constant is x squared on 3, and the ratio is x on 3. So therefore we can write the function as an infinite sum of the constant multiplied by the ratio to the power of n. And you can simplify this further by adding the exponents. So there'll be x to the power of n plus 2 over 3 to the n plus 1. And note that the geometric series converges when the absolute value of the ratio is less than 1. So therefore we obtain the absolute value of x is less than 3, and therefore the geometric series converges over the interval from minus 3 to 3. Let's show that the sum of the alternating harmonic series is the natural log of 2. Well, we can expand this series as follows, and writing this series in a simplified form, where we're basically just flipping the signs of the terms. So this is just a power series evaluated at one end of the interval. And we can expand this as follows, and differentiating it. So this is a geometric series with a equals 1 and a ratio of x. So it can be written as an analytical function. And then separating the variables and integrating, we can use u substitution to evaluate this integral, so the function can be written as follows. And we can see that f of 0 is 0, so the constant of integration just drops out. So if we sub x equals minus 1, then what we get is this series is equal to minus the natural log of 1 minus negative 1, or the natural log of 2. And if we multiply through by negative 1, we'll get the following result. And this here is effectively equal to our original harmonic series, which sums to the natural log of 2. We showed that the alternating harmonic series is conditionally convergent, and its sum is the natural log of 2. Show that the series sums to another value by rearranging its terms. So let's expand a few terms out of this series. And now we group some of those terms, so the fractions subtract nicely. And now evaluating the terms in the brackets, we obtain the following result. And now we can factor out the half. So now we recognize that this is the alternating harmonic series, which has a sum of the natural log of 2. So by rearranging this series as follows, we obtain a sum that's half of the natural log of 2, which is not equal to the sum of the original series.